establish a scale that is now called the Loeb scale, where 0 implies a natural object, definitely behaving like previous comets or asteroids, and 10 implies a technological spacecraft and a functional device that could threaten Earth. And at the moment, I would rank this object as 4.
Recent observations of the interstellar object 3I/Atlas revealed an unusual reddish coma, a cloud of gas and dust surrounding the nucleus. This coloration differs from typical comet appearances, which usually display more neutral or bluish hues. The reddish appearance represents one of several distinctive characteristics that have drawn scientific attention to this particular interstellar visitor. Comets can indeed display various colors based on their chemical composition and the specific materials sublimating from their surfaces. The reddish tint likely results from organic compounds and dust particles in the coma, particularly carbon-based molecules that absorb blue light more readily than red wavelengths. This selective absorption creates the observed coloration when sunlight interacts with the coma material. The color variations in comets provide valuable spectroscopic data about their composition, formation environment, and evolutionary history. Different regions of a single comet can even display multiple colors simultaneously, as various compounds sublimate at different rates depending on solar heating and internal structure. The reddish hue specifically suggests the presence of complex organic molecules, possibly including tholins, organic compounds formed through radiation processing of simpler molecules over extended periods. Claims of a blood-red cloud stretching thousands of miles and descriptions of cosmic nightmares are dramatic embellishments not supported by actual observations. While comets can develop extensive comas and tails, the apocalyptic language used in popular descriptions often misrepresents the actual scale and appearance of these phenomena. Real astronomical observations describe color variations in technical terms based on spectral analysis rather than emotionally charged descriptions. The blood-red characterization appears to be a sensationalized interpretation of what would more accurately be described as reddish or orange-tinged coloration visible through specific filters and wavelengths. Spectroscopic analysis indicated higher than typical carbon dioxide concentrations in the object's coma compared to water vapor, a ratio uncommon among solar system comets. This elevated CO2 to water ratio represents a genuine observational finding that distinguishes 3I/Atlas from many comets originating within our solar system, where water ice typically dominates the volatile composition. Some comets do show CO2-rich compositions, particularly those from outer regions of planetary systems where carbon dioxide can remain stable in solid form at greater distances from their parent stars. This compositional variation reflects different formation temperatures and chemical environments within protoplanetary disks. Carbon dioxide sublimates at lower temperatures than water ice, making it more readily detectable in certain observational conditions. The elevated CO2 levels in 3I/Atlas could indicate formation in a particularly cold region of its original stellar system or around a star with different thermal characteristics than our Sun. However, claims of nearly pure CO2 emission at industrial rates are exaggerated and not supported by published spectroscopic data. Real measurements show elevated ratios, not complete domination of one compound over another. The actual CO2 to water ratios observed, while unusual, fall within ranges that can be explained through natural formation processes in diverse stellar environments. Actual outgassing rates for comets vary enormously based on size, composition, solar distance, and activity levels, with measurements typically expressed in different units and contexts. Professional astronomical literature provides outgassing estimates through careful analysis of spectral line intensities and coma expansion rates. Initial size estimates varied significantly, with some suggesting a nucleus potentially 28.5 miles in diameter. The object's brightness behavior didn't match standard comet models as it approached the Sun. These discrepancies highlight the inherent challenges in characterizing distant, rapidly moving objects using ground-based and space-based telescopes with limited observation windows. Size determinations for distant objects are genuinely challenging and often revised as more data becomes available through improved observational techniques and longer observation periods. Brightness variations can occur due to irregular shapes, composition differences, or fragmentation events that alter the object's cross-sectional area and reflective properties. Astronomical objects rarely conform to perfect spherical shapes, and their rotation can cause periodic brightness changes as different surface areas become visible to Earthbound observers. Additionally, the relationship between brightness and size depends heavily on the object's albedo, its reflectivity, which varies dramatically based on surface composition and texture. A dark, carbon-rich object appears much fainter than a bright, icy one of identical size, leading to potential size estimation errors. Fragmentation events common among comets under thermal stress can temporarily increase brightness by exposing fresh, more reflective internal material while simultaneously reducing the apparent size of the primary nucleus. The complex interplay between distance, phase angle, surface properties, and activity levels makes accurate size determination a sophisticated analytical process requiring multiple observation techniques. Like many comets, 3I/Atlas underwent fragmentation as it approached closer to the Sun, a common occurrence when internal stresses from solar heating exceed the object's structural integrity. This breakup process represents one of the most frequently observed phenomena in cometary astronomy, with dozens of documented cases showing similar patterns of structural failure under thermal and gravitational stress. Comet fragmentation is well documented and occurs regularly across different comet populations, from short-period comets like those originating in the Kuiper Belt to long-period visitors from the Oort cloud. Fragments often continue traveling together initially before gradually separating due to small velocity differences imparted during the breakup event. The fragmentation mechanism typically involves thermal expansion causing internal pressure buildup, structural weakening from repeated heating cycles, or tidal forces during close solar approaches. Historical examples include Comet Shoemaker-Levy 9's dramatic fragmentation before impacting Jupiter, Comet Lineare's breakup in 2000, and numerous other cases where astronomers have observed and studied the fragmentation process in real time. The fragments usually retain similar orbital characteristics initially, creating temporary comet families that slowly disperse over months or years. Modern observational capabilities allow astronomers to track individual fragments and study how their properties evolve differently based on size, composition, and structural characteristics. This fragmentation data provides valuable insights into comet internal structure and formation processes.
3I/Atlas follows a hyperbolic orbit, confirming its interstellar origin, meaning it came from beyond our solar system and will not return after its current passage. The hyperbolic trajectory represents one of the most reliable indicators of interstellar origin, as objects gravitationally bound to our Sun follow elliptical paths that eventually bring them back, while interstellar visitors maintain velocities exceeding solar escape velocity throughout their passage. This makes it part of a rare category of interstellar visitors, following Oumuamua 2017 and 2I/Borisov 2019, representing only the third confirmed interstellar object detected passing through our solar system. The rarity of these detections reflects both their actual scarcity and the observational challenges involved in identifying objects that spend relatively brief periods within telescopic range. Detection requires objects to be large enough and active enough to reflect or emit sufficient light for ground-based or space-based surveys to distinguish them from background stars. The growing catalog of interstellar visitors results from improved sky survey capabilities and automated detection algorithms that can identify moving objects against stellar backgrounds. Statistical models suggest many more interstellar objects pass through our solar system undetected, particularly smaller bodies that lack the brightness necessary for current observational systems to identify. Such objects provide valuable opportunities to study material from other stellar systems, carrying chemical signatures from their formation environments billions of years ago and potentially millions of light years away. These cosmic messengers offer direct samples of material processed under different stellar conditions, with varying metallicities, temperatures, and radiation environments that shape their composition during formation. Comparative analysis between interstellar visitors and solar system objects helps astronomers understand the diversity of planetary formation processes throughout the galaxy. The isotopic ratios, mineral compositions, and volatile inventories preserved in these objects serve as time capsules, documenting conditions in their parent stellar systems. This research contributes to broader understanding of galactic chemical evolution, planet formation mechanisms, and the potential habitability of exoplanetary systems with different chemical characteristics than our own solar system. The fragmentation of dwarf planets or large moons in other stellar systems could theoretically produce objects with unusual compositions, but this hypothesis requires specific evidence, such as isotopic signatures, mineral assemblages, or structural characteristics consistent with differentiated planetary bodies. Without such evidence, this remains pure speculation among numerous possible origins. 3I/Atlas is indeed an interstellar visitor with some unusual observational characteristics that merit scientific study, including its confirmed hyperbolic orbit, distinctive composition ratios, and fragmentation behavior under solar heating. Interstellar objects like 3I/Atlas genuinely represent remarkable opportunities to study material from beyond our solar system. What other wonders does the universe contain in its vast expanse? Well, that is it for today's video. If you are still here, it's because you enjoyed the video. Do us a favor by liking this video and subscribe to the channel for more amazing contents that we will be uploading on this channel.